Hi everyone, my name is James Larson, and I'm going to be giving my final project presentation on hyperspectral imaging of tomato plants. The two questions I set out to answer with this project were, can carbohydrate stress be detected in tomato plants using hyperspectral imaging? And are there differences in spectral signatures between leaves in the top of the plant where fruit are located and then compared to the whole plants? To answer these questions, I had 8 tomato plants that were growing in a greenhouse, and then I imaged them with a Resonon Pica XC2 hyperspectral camera with a spectral range of 400 to 1000 nanometers and a resolution of 1.3 nanometers. These plants were imaged on 2 dates, January 30th and February 20th. After immediately filing that first imaging date, 4 of those plants had all the fruit or had all the flowers taken off of them, so that we were left with 4 plants with flowers and then 4 plants without. So this was meant to create a scenario where the plants with fruit were going to be more stressed for carbohydrates because they had developing fruit. After I imaged these plants, the raw data was ran through a Python pipeline that selected just the vegetation. And then from the reference cube that was also in the image, the data was corrected in R, and then spectral plots were made, and vegetation indices were also calculated in R. Then to do that area selection, I used Spectron Pro, which is a software that's associated with the hyperspectral camera. So here's that workflow. I took the raw data that's output in a .bil file from the camera and took it into a preprocessing pipeline in Python that selects just the vegetation and the reference cube that's in the image and calculates the mean reflectance value for each wavelength and outputs a CSV file for the plant and the reference cube. Those two files were taken into R, and the reflectance of the plant was corrected from the values of the reflectance cube. And then spectral curves were made, and vegetation indices were calculated also in R. That area was selected in Spectron Pro. Here I selected a small area in the top of the plant where the fruit were done, and this saves as its own .bil file from Spectron Pro, and then that could be reran through the processing pipeline. So here are those reflectance curves for each plant. Here on the left we have the whole plant, and then on the right there's the selected area. Fruit is in green and no fruit is in orange. You can see in the visible portion of the spectrum there's really no difference between the two treatments. There is some separation in the near-infrared portion, but none of that can really be attributed to a treatment effect. Here in the selected area, the differences are slightly more pronounced, with the fruit plants reflecting more light in the green portion, and then having a really variable response in the near-infrared portion. And as you can expect from not having much differences in reflection curves, you also won't get much difference in vegetation indices. That's what we see here between these two plots. The values are basically the same between fruit and no fruit. So my conclusions were that I really couldn't detect any differences in spectral reflectance that could be attributed to treatment effects. This is likely because the experiment wasn't able to be carried out long enough for that second imaging date. There was really only small fruits on the plants with fruit, so those plants weren't probably all that stressed compared to the plants that had no fruit. And I was planning on doing another imaging date later on when the fruit would have been larger, and theoretically the plants should have been more stressed for carbohydrates, but due to the shutdown, that wasn't able to happen. So this did create an easy-to-use workflow that could take raw hyperspectral imaging data and put it into a format that's easily workable in R to visualize reflectance curves and calculate spectral indices.